Okay, so let's take a look at question 4b from the 2010 scholarship paper. It's a redox chemistry question, which I'm starting to really like these questions now. And it's in context as well. So gold and silver are extracted from finely ground ore by complexing with cyanide ions to give soluble complex ions, where M represents the metal, and that's going to be either Ag for silver or Au for gold. Um, so Au for gold. Um, Gold ore occurs in its elemental form, and silver is found in plate in the same deposits as silver sulfide. Now, silver sulfide is Ag2S, and that's solid right there. Just for a bit of more context to this, the first time I read about this process was when I was in the Coromandel for the first time. And there's a little billboard if you're down at the, hopefully pronounce this the right way, the Karanga Hake Gorge. There's a little placard describing this actual process. So yes, in the Coromandel, this process is described on that particular billboard. If you're ever in that gorge, take the time to look at it, and hopefully you'll understand the chemistry when you read it after watching this video. Now, there's a lot of more information that follows. Sodium cyanide solution is sprayed over the ore in the presence of oxygen. So sodium cyanide solution is just NaCN, aqueous. In the presence of oxygen, so O2 gas, soluble sodium dicyanoorate. So that's that complex right there, and sodium dicyanoarginate, which is that complex there that sounds like two types of dinosaurs to me, are collected. The process is carried out at pH 10.5. Then you're given 5 different reduction half equations here with the standard reduction potential values given to you. You're given the Ka for cyanic acid, which is 6.17 by 10 to the minus 10. So all of these numbers and equations have some relevance, as we'll see when we answer the question. And then the target is show using the electropotential values given above that the recovery of gold by the cyanidation process is preferred to the possible alternative of dissolving the ore in hydrochloric acid. So that's the first thing we need to do. Include balanced equations in your answer, so that's there. The second thing we need to do is discuss the difference in the chemistry of the recovery of gold. Okay, so the second part is to discuss any differences in the chemistry of the recovery of gold and silver by the cyanidation process. And then they also want us to mention why the process is carried out at a pH of 10.5. So what I've done here is I've laid out a new page, and I've drawn a little diagram to represent what's happening in this actual physical process. So gold and silver are being extracted from finely ground ore. So these little blobs here represent that's an ore of gold. This is an ore of silver sulfide. So they're extracted from those ores by complexing them with cyanide ions to give soluble complex ions. And gold occurs in its elemental form, which is Au solid, whereas silver is found in some of the deposits of silver sulfide, Ag2S. Sodium cyanide solution, which is this stuff here, is sprayed over the ore in the presence of oxygen. So oxygen is also present here as you spray them. O2 gas right there. And soluble sodium dicyanoorate is what you get for the gold. So this is your sodium dicyanoorate right here. And then sodium dicyanoarginate is what you get here for the from the silver ore. These are collected and it's carried out at a pH of 10.5. So a pH of 10.5 will be useful later. So we'll just write that down, pH of 10.5, and that tells us that the concentration of H3O plus is going to be equal to 3.16 by 10 to the minus 11 moles per liter. So that's important to know about that, and we'll understand that later. So what do we need to do here? The first bullet point then is just to move back a step. I've said this before with other videos. Make sure you have the exam question printed out in your hand as you watch these videos, because I'm not going to refer back to the exam question over and over again to show what step I'm moving on to. So the first bullet point anyway was to show using the electrode potentials given in the list that the recovery of gold by the cyanidation process is preferred to the possible alternative of dissolving the ore in hydrochloric acid. So I'm just going to take my page. So we're focusing on the gold situation here. And what we're saying is there are two ways to extract that gold from that ore right there. The first way is to use the cyanidation process, which is this process that we have here, versus the alternative, which is to take the ore and dissolve it in HCl. So we need to compare these two processes and see, using the reduction potentials, why the cyanidation process is preferred over the dissolution in HCl acid. So that's what we're going to take a look at now. Something else I forgot to do just before we move on to that was, when we have this little diagram set out like this, it's quite nice to assign oxidation states. So the gold here has oxidation number in its elemental form of 0, whereas in the complex then it's going to be +1 right there. In the silver, the oxidation state is +1 to start with, and it also ends up as +1. So there's no redox chemistry relating to this process for the silver cyanidation, but there is, in this case, we have oxidized the gold in that process in order to form its complex there. So the redox, this is why the redox chemistry only applies to the gold process when we're doing cyanidation. And you'll see why that's relevant then for one of the explanations we need to give later. So for the cyanidation of gold, we want to look at equation number 2 and equation number 4, because equation number 4 has your gold solid to start with and your cyanide ions, which would come from your sodium cyanide solution, which is sprayed over the gold. The solid AU is in the ore, so that's why we use equation number 4. And we use equation number 2 then as well, because this is the oxygen which is present in the process, and it's described there, sodium cyanide. There you go, the cyanide from there. Solution is sprayed over the ore in the presence of oxygen, so that's why we use equations 2 and 4. For the other explanation, the ore being dissolved in hydrochloric acid, well, there's two possibilities there. You're definitely going to use this equation number 5, because that's the source of H plus is coming from your HCl dissociation. And then there are two possible other equations you could consider. You could consider equation number 1 there, where your AU solid is oxidized to AU plus, or alternatively your AU solid is oxidized to AU3 plus. So when we look at the HCl dissolution of the ore, we consider equations 1, 3, and 5. When we're doing the cyanidation, we're considering equations 2 and 4. So this is what we're going to focus on now. So it's really a case of spontaneity. So if we take equations 2 and 4, the E0 value for equation 2 is plus 0.40 volts, and that would be for the reduction of oxygen to and water to 4 hydroxide ions, if you have your paper in front of you. The E0 value for equation 4 there is negative 0.60 volts, and that's for the reduction of silver in its complex, or gold in its cyanide complex, to gold solid and to cyanide ions. So if we do the highest reduction potential value is the one which will be reduced. So E cell for this particular reaction would be equal to plus 0.40 volts minus negative 0.60 volts, which is equal to an E cell of 1 plus 1.00 volts, which means this reaction is spontaneous. And it's spontaneous in the sense that equation 2 is the reduction half equation, and equation 4 is going to be oxidation. It's going to be oxidized. So what that comes out as is equation 2 is oxygen plus 2H2O plus 4 electrons going to 4 hydroxide ions. So that would prefer to be reduced. And the other equation then, the gold plus the cyanide is being oxidized because it had the much smaller reduction potential value. And so that's what forms your gold cyanide complex there, plus a loss of an electron. If you want to write a full balanced equation for that, which was required in the exam question, then we're just going to get rid of our electrons there. So we multiply everything by 4 here. So it's 4Au, HCN minus 4 of those and 4 electrons. You cancel your 4 electrons out, and you get 4Au plus oxygen plus 8 cyanide ions plus 2 water molecules going to 4 hydroxide ions, plus your 4 gold cyanide complex ions. And that reaction is spontaneous. It does happen. So now we need to compare that process to using the ore and dissolving it in HCl. So if we do it with HCl, let's just use red for an acid here. HCl, remember, is a source of H plus ions, so that's why we're looking at equation 5 for that one. Equation 1, remember, there's no cyanide involved in this process. This is the alternative to using cyanide. So we have to look at equation 1 first of all. The E naught for that is equal to plus 1.83 volts. And the E naught for reduction of protons, which is the standard cell for reduction potential measurements, that's equal to 0.00 volts. So this species would rather be reduced, and this species would rather be oxidized if we have the 2 of them in solution. The E cell for that is going to be equal to, so if we want the reduction of H plus from H plus to hydrogen gas, if we want that process to actually be able to happen, then the E cell is going to be 0.00 volts and minus 1.83 volts, which is equal to negative 1.83 volts, which is non-spontaneous. And I can see that from just writing the E naught values down here, this process would rather be reduced and this would rather be oxidized. So that reaction is non-spontaneous if you combine equations 1 and 5, for the simple fact that the E naught value is much greater for equation 1. So the gold ions, if they do form, they'll be immediately reduced back to solid gold, which is getting you nowhere because you needed to get the gold ions to complex them with the cyanide. So scratch that last comment about the gold ions complexing with the cyanide. There's no cyanide present in this process, but what we have here is our gold ions not being formed. You're staying as solid gold, which doesn't help you extract it from the ore. It's still stuck in the ore. The other alternative there is to look at equations 3 and 5. It's a similar situation. For equation 3, you're considering Au3 plus ions, and the E naught value for that is plus 1.52 volts. The E naught value for our H plus to H2 gas is still 0.00 volts. If we're talking about H plus being reduced again to H2 gas, plus 2 electrons, then that is going to be our reduction right there, and that's our E oxidation. And the E cell for that process is equal to 0.00 volts minus 1.52 volts, which is a negative value as well. So this would be a non-spontaneous reaction. Again, so in other words, the species with the higher reduction potential is going to be reduced. So the Au3 plus will be reduced back to Au solid, which means it's still trapped in its ore, which is no use to us in the extraction process. So that's why the cyanidation process is preferred over dissolving the ore in hydrochloric acid, which was the first part of the question that we needed to answer. And we included a balanced equation where we could, which was for the spontaneous reaction. Now, the second part here, discuss any difference in the chemistry of the recovery of gold and silver by the cyanidation process. So if we go back to our little diagram that we drew up at the start at the top here, the answer to this is essentially that the reaction for the cyanidation of silver from silver sulfide to its silver complex is not a redox reaction. So it's not a redox reaction because the oxidation state of the silver doesn't change from one species to the other. And also there's no oxygen involved. There's no oxygen involved in that reaction again because it's not a redox reaction. So we can check the NCA answer just for some more clarity on that. The reaction with gold is an oxidation reduction reaction in combination with a complexation, which is the metal cyanide complex, requiring the presence of oxygen as an oxidant. The complex formation reaction with silver sulfide is not an oxidation reduction reaction, as the oxidation number doesn't change and does not need oxygen to proceed. And then the last part of the question, we're just going to look at here, discuss why the process is carried out at a pH of 10.5. Well, we just need to take a look at this Ka value, which could quite easily have been overlooked at the beginning there. That is for the dissociation of cyanic acid, which is a weak acid, and that will form cyanide ions, which we need for the cyanidation process, and some hydronium ions. If you have a pH of 10.5, that gives you a concentration of H3O plus of 3.16 by 10 to the minus 11 moles per liter, which we worked out at the beginning. And that's a very low concentration of H3O plus. That's a very low concentration. If we can reduce this concentration, then that means we can pull the position of equilibrium over in this direction. So that's just Le Chatelier. If you reduce the concentration of your product, then you need to make more product by decomposing the HCN. Now, the benefit of that is that we'll get more cyanide ions, which are then available to form the metal cyanide complex, which we're doing here in this process with either the gold or the silver to extract it from its ore. So the benefit of the high pH is to keep the concentration of H3O plus down, which then pulls the equilibrium across this way to make more cyanide ions available. And as the NCA guys say, the Ka value of HCN is that at a pH of less than 10.5, the concentration of H3O plus would be high enough to allow the formation of HCN, which is not what you want. The pH above 10.5, however, would maintain the maximum concentration of cyanide ions in solution and maximize the dicyanoorate complex formation. So that's a nice question. And as I say, that process was used back in the day when the guys found it difficult to extract gold and silver ores from the mines in the Coromandos. So check it out next time you get a chance to read some of those information signs. And that was question 4, part B from the 2010 scholarship paper.